Okay, finally, the most important part, as known as the main course of chapter 3, which is the ideal gases. So you should have heard of the ideal gas law, which is the equation PV equals to nRT. Let me put it down here. So PV equals to nRT. Or at least in IGCSE, you should have heard about things like Boyle's law, PV equals to PV, 1122, or something like the Charles law or pressure law, which could be derived from ideal gas law. So historically, of course, we have Boyle's law, and then Charles law, and then pressure law, as known as Gauge's law, if you know about the guy's name. And then we could try to combine or unify that three law into the ideal gas law. So this is the mathematical expression of ideal gas law. But more fundamentally, what IB will expect you to understand and know is what are the assumptions under the ideal gas law, because ultimately ideal gas are ideal. I mean, it only works in certain scenario. Similar to chapter 2 when you learn about mechanics, when we talk about free falling, acceleration is only 9.81 under certain scenario. That could be probably is there's no air resistance, etc. So we have to understand very clearly as a physics student or physicist what are the assumptions underlying our theory. Okay, so I want you to read the textbook right now, and I will hope you can answer, and you should try to answer this question and this question in your question set. So you should start from reading from this up until the next half page, until before the pressure volume law here. Okay, so you may want to pause the video and go and try to answer the question right now. Okay, so the first question that I asked you in the question set is I want you to state 4 main assumptions of ideal gas. So you may have done it already, but what I mean, you can see here there are 6 points, right? So if you only simply without any thinking just copy these 6 points into this, then I will want you to rethink again. So if you really did 6, like all of them without thinking, let me challenge you. I will want you to guess which 4 are the one that I would personally think would be the best answer out of these 6, and also try to use keywords instead of just copying the whole sentence. Try to find out what the keywords are and try to write it down here, because ultimately you want to digest the concept and you want to make it more concise, so when you study it's much easier in that case. So if you haven't done that, do it now. So let me take a look of these 6 assumptions that mentioned by the textbook, and I will go through the one that I think is the most important. The first one that is said is particles are point particles. Sorry, the molecules are point particle, which means they have negligible volume, and this is one of the point that I think it will be very important. But let me use a thinner highlighter. Okay, so this is the one that I would say is a good one. You may even say the volume is negligible is a good one, or you can say even no volume, because technically point particle has literally no volume. The reason why we need this we will be able to explain later on when we try to prove some other equation later on. So for now, I think you just remember this first. I would say you can just simply acknowledge this, and then later on in the future when we try to prove another one very important equation, then we'll come back to this again, and you really understand why the volume should be negligible. So that means whenever you are dealing with a particle that has a large volume, then the ideal gas law may not apply. Okay, so let me take a look of the next one that I think would be more important. The second one, saying obey laws of mechanics, I don't think this is a good one because it's just too general. So if you have a chance in the exam, they ask you state, they will really do, like it's actually quite often, they will ask you to state the assumptions of ideal gas with maybe 3 marks. Apparently you have to write 3 assumptions. Then this is not the one I would like to write, like obey laws of mechanics, cause I really don't think this is too specific enough. But of course, I mean, if you could add some more, simply just to be safe, add this at the end of the suggestions that you are trying to make. The other one is saying there's no force between the molecules except when the molecules collide. Actually, I'm not sure if you understand this sentence, but this is one of my choices I would suggest. So first of all, what do you mean by no forces between particles normally? And also, what is the force that molecules collide? Think about there's a simulation which I will show you later on. So when you try to have some gas particle, then what you have is the particle in itself, between them, they will collide with each other. So when you have the particle collide with each other, then they must exert the force between each other, like the impact force between the molecules. And this is very obvious, of course, but other than that, there is actually some other force. If you think a more formal way, like practically, there are some other force. Think about what kind of force will be between the molecules. Of course, I know molecules and container, yes, there will be impact force also, but what are the other type of force between molecules to another molecule? Okay, here's my answer. Think about this. All those particles or molecules, they are actually composed of the same entity we call proton and neutron inside the nucleus, and outside, you know, they are electron. At least so far you should know about this. And if you think about different particles, they will have the electron repelling the electron also. So that will be one of the force. Another force is called the Van der Waals force, which you may learn in chemistry, which is this one. And in fact, I actually mentioned it in the previous video in chapter 3.1 part 2 as well, if you remember. So these kind of forces will actually exert between the different each particles, or you may say molecules. And in our ideal gas law, or we treat them as long as we treat them as ideal gas, then this force is basically ignored. Or the other way, that is to say, if this force is going to be very significant on the gas you are trying to analyze, then ideal gas may not be a good model to estimate, to predict what will happen for that particles. So once again, this is also a very good one. No force again between the molecules except when they collide with each other. Oops, I delete all the markings. Okay, so the next one is the duration is negligible for the impact compared to the time between the collision. So what it means is actually saying that when you have the collision, there must be a collision time. So like when you play tennis, the racket will hit. Okay, I'm not a very good drawer, but let's say the ball going to be hit by the racket, there must be some duration of the impact time. So same for the particles between each other. But here we will again in the future we will explain more of why this is important. But then right now you may firstly recall, so whenever they collide, yes, they still have impact force and they have collision, but the time for that will be very insignificant. Probably let's say it's 0.01, while the container itself, because it said compared to the time between the collision. So imagine the particle has to travel back, this particle have to travel back to collide again, and maybe that time will take, say, 1 second. So if you compare 1 second to 0.01 second, then 0.01 is kind of insignificant in that case. So that means you can ignore it. Okay, so be careful with the wording here, which you may need to memorize. Actually, I would suggest you to memorize it. Number 4 is referring that the collision are elastic. So again, this is one of them, one of the assumptions that I would recommend. And I think elastic is really the only important word. We are talking about the collision between molecules to molecules and also molecules to container. So there are two kind of collision. Be careful. You can, if you try to see more carefully, molecules with each other and molecules with container. Two kind of collision. Both of them are elastic. And in case you don't remember the word elastic, it actually means that there's no KE loss. Okay, so in other words, if you try to put it in a more macroscopic view, that means the temperature over time, since you don't lose any KE, right? So that means the overall KE in a container for all the particles, if you try to sum up all the energy, it will remain constant because you never get any energy escape from the container. So nothing, no energy is going to go out of this or that, or you may say there's no energy loss in the surrounding, etc. So that means the temperature remained constant over, I mean, basically forever in that case. And of course, you know, in reality, it is not the case. It would slowly cool down probably. So that is the assumption you need to have. Okay, so apparently the last one is one of the assumptions that I would not recommend to put first. Although it is true that they will move randomly and they will have a range of speed, but I think this is very obvious. Some of them, of course, move faster. Some of them will move slower, and of course, they are all moving in random direction. So these 4 should be the one that you have put down. So if you haven't, or if you chose something else, try to change them, because this is going to be very useful for your revision. Okay, second question that I asked you is what condition can real gas behave like ideal gas? So if you try to think from the ideas here, or you simply try to read the paragraphs in the textbook, you will find that real gas will behave more like ideal gas when the density is low. Okay, and you may ask, so how can we well, other than memorizing, can we somehow prove or derive, or at least try to deduce from the assumption? If you can remember the assumption, then you should be able to deduce density is low. So here, let me show you how to do it. Think about this. When we say the volume is negligible, which actually means you may say no volume, but of course you cannot have particle that does not occupy any volume at all, right? So it must contain very, very little at least of volume comparing to the container. So imagine you have a big container and you only have like very, very tiny dust like size of particle inside in, say, a aquarium or something. And so in that case, if you try to calculate the density of these particle, dust-like particle, then of course the density would be low in that case. All right, so if you could remember or recall density is low for the real gas to behave like ideal gas, then you can further deduce about its temperature. Okay, if you try to skim through the textbook, you may see the word low temperature, but then don't get yourself wrong. It actually means that it would not behave like ideal gas when this is at low temperature. If you try to use the logic to deduce, then you can actually tell quite easily. Since we already understand the density has to be low in order to behave like ideal gas, then think about this. When temperature increase, what will happen? The speed, since you learn about temperature actually related to KE, and then the speed will increase. Then think about if the speed increase, then generally the separation between the molecules would also be higher, and in that case, of course, the density would be lower in that case. So higher temperature is actually the way to go. So So the lesson learned is it's better to deduce and also try to read the full sentences if you can. So this is another thing that you may want to see, and or you can try to simply refer to here. It's at high temperature. The other thing that you should refer to is what about the pressure then? The pressure for real gas to behave like ideal gas will be low. So it will be the similar idea where only when the pressure is low, then they are more separate. Think about when you go to take the bus or MTR when there are so many people around you, and that means the density is high, then of course the pressure is high. So in that case, that doesn't help you to help the real gas to behave like ideal gas. So in that case, pressure has to be low, temperature has to be high, density has to be low. In that case, in order for real gas to behave more like ideal gas. Okay, so for summary, I would say I will prefer the best way to do is to remember these assumptions, especially these four, and then from that you can deduce density is low, and from density is low you can deduce about the temperature and also pressure. Okay, so try to jot down some notes here to help you to organize the idea, and we'll talk more in the next video.